All right, welcome back to the most loaded video I've probably done to date, where we are going to be talking about the coordinate plane and symmetry in both graphical and algebraic representation of functions. It's going to be actually a two-part video because there is just so much and I might need way too much time. So we're going to break it up into two parts, parts 1 and 2. Here is our vocab, as you can see, pretty lengthy. We're learning to identify orally features that graphs of even functions have in common and features that graphs of odd functions have in common. So I'm going to explain orally how to sketch the second half of an even or odd function given the first half. I'll know I've got it when I can justify orally and in writing why a function is even, odd, or neither from an equation. The bulk of that will happen in our part 2, but in order to have that conversation, we must first tighten up the beginning, I guess you could say, of the coordinate plane. So just as points on a line can be identified with real numbers to form the coordinate line, points in a plane can be identified with ordered pairs of numbers to form the ordered pair or coordinate. Any point P in the coordinate plane can be located by a unique ordered pair of numbers, AB, where the first number A is called the x coordinate, or I'm missing an R. Man, rough day. And the second number B is called the y coordinate. So, share with the class, and let's recall some basic information. Describe how the coordinate plane is constructed, include a description of its major components, x-axis, y-axis, origin, and quadrants. Input all of that information into this text box here. And on the graph to the left, label the x-axis, the y-axis, the origin, a unique point with coordinates, so like a point like this. And then make sure you put, the coordinates in a similar location, and then quadrants 1, 2, 3, and 4. And before I forget, because I typed this here, read. Coordinate plane is the link between algebra and geometry. In the coordinate plane, we can draw graphs of algebraic equations. Graphs, in turn, allow us to graphically, I think that's what, because my camera's blocking it, notice a relationship between the variables in the equation. All right, first things first, we have distance, and that involves being able to calculate a midpoint. So there are lots of information going on here. Okay. But if we want to calculate the distance between 2 points, A and B, right, we would first need to calculate the horizontal change and the vertical change. And if you remember anything from your time in geometry, hopefully it wasn't traumatic, you'll see both the horizontal and the vertical change, including the distance between those 2 points, creates a right triangle. So we're going to use the foundation of the Pythagorean theorem to help us out here. So the distance is given by square root, because it's the Pythagorean theorem says to take this, to square the two legs, add them together, and that's going to be equal to the hypotenuse squared, right? But in this case, the hypotenuse, we just want its length. We don't want its length squared. So we're going to square root the square of the legs being summed together. So that first leg, right, is going to be x2 sub 2. So in case you're wondering how am I doing that, I'm pressing shift and then minus power, right? That's that first leg squared plus I'm going to replicate that process by sub 1 squared, right? And that is my second leg squared. And then obviously, once again, the square root is because we are not squaring the length of the hypotenuse here as the way we would with the Pythagorean theorem. Right, and that will give us the distance between those two values. As for the midpoint, I can get into this long-winded explanation about how, this point comes from similar triangles, congruence theorems, but we're going to avoid all that. So with the middle, I want you to think of the word average. Okay? Because basically when we were calculating a midpoint, we are taking a graphical average of the coordinates. So in order to do that, or to calculate an average, you should remember, comma, taking averages involves you dividing by the amount of terms that you are summing. In this case, we have 2 points. We're going to divide by 2. And to get the midpoint of the x coordinates, we would have to sum those x coordinates. Our life easier. And then for the y coordinate, we would do the same. So a little conceptual walkthrough as to how we arrive at this distance and a formula for midpoint. So first and foremost, please determine what the distance is between the points -5, 6, and 3, -5, and then determine the midpoint of that line segment between those 2 points. And let's get into the nitty-gritty. All right, so the graph of an equation in x and y is the set of all points, comma y, missing that first parenthesis, and the coordinate plane that satisfy the equation. Right, so this is kind of this idea of tethering algebra with a graphical representation. Cool. The x-coordinates of the points where a graph intersects the x-axis are called, yes, you named it, those are our x-intercepts. And the y-coordinates, the points where the graph intersects the y-axis, are conversely known as the y-intercepts. So, 2 prompts here for you to respond to. Explain what you remember about how to graph an equation. Try to tease out all of those words that you used freshman year and in Algebra 2. That you took Algebra 1 as an 8th grader. So whenever you took Algebra 1, Algebra 2. Right? And then I'd like for you to explain how to algebraically determine the x and y intercepts of an equation. Okay? I know how I can do it graphically. I just look for where the graph crosses both the x and the y-axis, and voila. Very straightforward, not much to it. But what does that process look like algebraically? There's a unique characteristic of every coordinate on the x-axis, and there's a unique characteristic of every coordinate on the y-axis. Let's see if you remember. Because here, you'll be tasked with sketching the following equation and finding the x and y intercepts of the graph of the equation y equals 4x minus 36. I'm going to allow you to graph the equation however you deem fit, because I don't think there should be a standard way to graph a line. However you see fit is a-okay with me, so long as you get the same line. Now, as far as the x and y intercepts, if you take any coordinate along the x-axis, you'll notice that they all have a y value or a y coordinate of 0. So we're going to use that to our advantage. In finding an x-intercept, we're going to set y equal to 0. So if you didn't say it in the previous slide, you don't need to update, but something to keep in mind. So here I will make my equation y equals 4x minus 36. I've substituted a 0 for y because I'm looking for the corresponding x coordinate. I would obviously add 36 to both sides, and my new equation would look something like 36 equals 4x to which a divide by 4 will yield x equals 9. So the x-intercept, how I would like for you to write it, is 9, 0, because remember, an intercept is not a numerical value, it is a coordinate, and we should write it as such. I think your professors in the future will thank you, because I won't be there. So please handle the y-intercept and sketching that following equation. We're going to talk much more about this towards the end of the school year, but it's good to refresh your memory because you should have covered it in geometry, and if you didn't, that is okay because we are not doing too much of a deep dive. But an equation of a circle with center hk and radius r is strikingly similar, once again, to the Pythagorean theorem because circles are really triangles rotated. So, why do I have, yep, there we go, the draw tool. So first and foremost, we're going to take point on the circle, x, and subtract the value associated with the center, square it, sum that to the y value on the circle, minus the y value of the center, square that, set that equal to the value of the radius, and square it. Definitely similar to this Pythagorean theorem. Trying to see what's tying everything together. We call this the standard form, because we can obviously also write a circle. We can expand those factored forms and still have an equation of the circle. It's just much more difficult to identify the circle's components. If the circle of the center of the circle is at 0, 0, the origin, our equation is much more straightforward. Squared plus y squared equals r squared. Now don't forget that, because in about 3 months I'm going to ask you what happens, or what is the equation of a circle when the center is at the origin. So in this case, right, I'm going to assist you with the sketching the graph part, but ask you to work your way through finding an equation of the circle. So I can first and foremost identify that my center is at negative, there we go, negative 2, 1. Remember, the structure of a circle, or the equation for a circle, is that these values are negative. So this value dictates what the center is, and then this 4 represents r squared, which means my radius is really 2. So I'm going to plot that point, negative 2, 1, negative 2, 1, here. I know that my radius is a value of 2. So I'm going to have distance of 2 from the center, 2 from the center, 2 from the center, and 2 from the center. And I hope that I can make a nice circular. That is too far because this point would be 2 from the center. Can I erase a little bit? Oh, so close. What a beautiful circle. Right. So this is our little circle. Now, as far as creating the equation of the circle, right, the equation requires 2 components, the center and the radius. And here I give you the endpoints of the diameter. If you've forgotten, the diameter would be from one side of the circle to the other. However, the center of the diameter can best be described as its midpoint, and from there you should be able to find the radius of the circle. So I'd like for you to spend some time really thinking through that process rather than watching me do it, because merely replicating my procedures is not going to lead to a much deeper level of conceptual understanding. So this one is what we're going to tease out together before we take a pause on this video. So in this checkpoint, where you want to demonstrate that this equation represents a circle, and then to find the center and radius of the circle. Back in lesson 5, we covered a concept of solving a quadratic that is called completing the square. Can I copy this equation so I don't have to type it? Let's see, Control C, hit that square root button, voila. I'm going to rearrange my terms and collect things that are very similar together. What I want to do is I want to complete the square on my x terms, my y terms. I'm actually going to throw this constant onto the other side of the equation because it's actually my radius. So my equation is going to look dramatically different, but it's going to be structurally the same because what I am doing to one side of the equation, I will be doing to the other side of the equation. So I'm actually going to change this to -7 now and take that away from the left side. So I'm going to complete the square of these two terms. Okay. The way in which you should think about it is x plus what number and doubled will yield a 2x. That number, very straightforwardly, is 1. Now, as a constant, right, 1 to the second power is still a 1. So I'm adding 1 to my left side of the equation. And because mathematics is all about equality, I should make sure that I do the same to the other. That way, they're equal. We're going to reapply this process, however, it'll be y minus, because this negative 6y is negative, second power. So I want to think through what number, when doubled, will yield a 6. That number is 3. Or in this case, right, negative 3 to the second power will yield a 9. I'm adding 9 units to the left side of the equation, so I should also add 9 units to the right side. I simplify the right side of the equation. I will get -7 plus 1 plus 9 will yield a 3. Let's recopy that equation. And now look, we have a much more readily identifiable center, which will be -1, 3, and a radius that is, remember, that 3 represents r squared. So the radius will be its square root. Don't believe me? Graph both equations on Desmos, see what happens. And like I said, that's where we'll pause and pick up with part 2.